Today I'm going to be presenting on my AA 290 work over the last couple of quarters. It's going to be similar to, it'll be kind of similar to, Zara was just talking about imaging exoplanets, and now I'll be talking about imaging in a slightly different way in terms of interferometry. So as Professor D'Amico alluded to, this is really inspired by a proposal called Sci-Fi at JPL to kind of pave the way for unprecedented resolution images of things like black holes and key traces of planet and galaxy formation. This probably this is too much information to absorb right now. So today I'm going to take you through a little bit about what interferometry is, what I was hoping to achieve with this research, and then how I implemented it and what sort of results I was able to obtain. From a high-level standpoint, an interferometer simply measures the interference pattern between received electromagnetic traces at two apertures at discrete points. Using this interference pattern, we can obtain the source image or resolve the source image through a 2D Fourier transform. And so just to give you an example, something you all are probably familiar with, this image of the black hole that we obtained a couple of years back was produced via something called very long baseline interferometry, which is a common technique in radio astronomy nowadays to resolve these sorts of images. Generally, what we can have a schematic diagram here. This 2D Fourier transform occurs in the plane that is orthogonal to the target direction, something we call the UV plane. This will be kind of a key piece of information to understand moving forward. So we'll have two apertures in space, these red dots, and then to resolve the image, they'll receive some signal from the cosmic source. We'll project the positions onto this UV plane, and then take this interference pattern and then the Fourier transform to resolve the source brightness. So the key takeaway here is knowing the positions of our apertures in the UV plane and having our measured interference pattern, we have a direct link to the source image. And so that's kind of the key of this work. One way we characterize the resolution of interferometry and interferometric image is angular resolution. And so angular resolution is inversely proportional to the measurement baseline. So how far away these apertures are located, or in the case of many apertures, we take the maximum baseline. So this is great. We do interferometry now. You saw we got that black hole image, but what's the issue? So the problem is that Earth's atmosphere absorbs some of these traces of electromagnetic radiation, and it's prohibitive for studying the things that I mentioned on the first slide, like traces of star and galaxy formation. But if we want to move to the space regime and have spaceborne interferometry, monolithic spacecraft can't be large enough, or it's prohibitively too large to provide the requisite angular resolution. We can't separate the apertures far enough to increase the angular resolution to the scale that we need. So as you probably can imagine, we're in SLAB. The solution is distributed space systems. We'd like to replace this single monolithic spacecraft with a swarm of small satellites that can provide very large baselines on a scale of kilometers. They're all low size, weight, cost spacecraft. We can send many of them up. There's multiple apertures that'll give us great flexibility and reconfiguration for imaging, say, multiple targets, or just adapting to get multiple views of the same image or the same target. So with this all in mind, your crash course on interferometry, my research objectives here were to resolve a connection between our orbital motion, both absolute and relative, and coverage of the UV plane. Remember, we have a link between our samples in this 2D plane and the source image. And so if we can resolve this connection, this should be able to help us help inform us as to what the optimal configuration should be for imaging. So as I mentioned, the second point is to actually determine these optimal nominal orbits for UV plane coverage. And then upon seeing what the optimal unconstrained configuration is, refine the results, consider minimum propellant consumption formations, as well as passive safety constraints. So setting up this problem, I'll I'm trying to keep this brief, so I'm not going to go through all of the gritty details, but I'll first connect this to interferometry. If we consider circular orbits, we know we can find in closed form that the absolute orbit motion in the UV plane will be some ellipse projected onto the plane. So we can think of, if the target is viewing our absolute orbit from an oblique angle, this circle in inertial space will be projected as an ellipse in UV space. And so this will be kind of an important or interesting to think about later when we see some of the optimal absolute orbits. You can start imagining, like, depending on which direction the target is facing, if we have an orbit that's edge on, we'll be getting a different or a much different coverage of the UV plane than an orbit that's rotated, say, 90 degrees or normal to the target direction. The relative orbit motion is much more complicated for the UV plane. This is a time-varying, nonlinear map that depends on the orientation of the absolute orbit, the target orientation, and the relative orbital elements. So I've just put the equations up here for, small separation, two-body motion, relative orbital elements, and relative Cartesian elements. Having these Cartesian elements, though, we can rotate from relative space to absolute, or a relative frame to an absolute frame, and then from this absolute frame to the UV frame. So it is possible to map relative orbital elements directly to UV space. It's just that the map is highly nonlinear and time varying, and I wasn't able to find a closed form helpful solution. Just an example of something that we could get here is this pattern here. This is an example of 3 spacecraft, their motion in the UV plane. And as you can see, there's no circles, there's no ellipses, it's twisted and turned and nonlinear. But so this is just to kind of build the intuition, what I found going through with this work. And so we'll move on now to what I've actually done with the optimization problem. When considering I should have broke this up, but considering the absolute orbit, we're only going to consider 2 angles for its orientation and the semi-major axis for its size. We're considering circular orbits or near circular orbits, so I've left the eccentricity and argument of perigee as well as the mean argument of latitude out of this to reduce the design space. For our relative orbits, we'll assume that relative semi-major axis is 0, and we'll leave all of the other relative orbital elements free for the solver. I'm going to be showing a 6 spacecraft swarm today. We'll take into account 2-body forces, J2 and drag, for a static inertial target. Let's see. It's also important to understand what is our loss function in this optimization. So we have 2 objectives that we're looking to optimize for. The first is UV plane coverage. So I've modeled this as a KL divergence. So if we consider this distribution P as our desired measurement distribution or distribution of samples in the UV plane, we can consider the best or optimal case, best case would be if we had uniform sampling at every point in the plane up to some discretization. We can take our set of sample points S and form a measurement distribution in this plane and then measure the divergence between our actual sampled distribution and our desired uniform sampling. So that's our loss metric for the UV plane coverage. And for the delta V, I've combined a couple of different terms for absolute and relative orbit delta V to account for drag and J2 perturbations. Since this study addresses nominal orbit configurations, we'll just assume that we'd like to do some orbit keeping, and those are the delta V terms that we'll consider. As far as constraints go, we need the measurement baseline to reach some minimum. As I mentioned, angular resolution is inversely proportional to measurement baseline. And so we can consider it a scientific objective to have some minimum baseline, as well as I've adapted some passive safety constraints from some of the papers from this lab. So this is, I won't do this in detail. This is from Adam Koenig's paper on spacecraft swarms. Great. The problem with passive safety, that's a good point. This constraint is computationally expensive. This is going to be one of the problems with optimization. So for a 6 spacecraft swarm, this passive safety constraint generates 15 constraints on the optimization problem, 15 nonlinear constraints. And so this is one of the problems we'll have to address going forward, but I wanted to highlight it here. So let's pop into the results. Since this is a multi-objective problem, I've generated a Pareto front here of results. The blue points are going to be for unconstrained optimization, so no safety constraints considered, and the orange points are the constrained Pareto front. And so just looking at this, it makes sort of sense. The orange points are not as great as the blue points, where the y-axis here is our delta V in terms of kilometers per second, and the x-axis here is our UV coverage. So as we move further to the right on the x-axis, we get worse UV coverage. And as we move higher on the y-axis, we spin into more propellant to maintain our formation and our absolute orbit. So I'll highlight here that for the single objective case, these are the 2 points that we obtained by only looking at UV coverage. See here that the constrained case, there's a lot higher delta V than the unconstrained case, but they're still similar in UV coverage. And I'll contextualize this UV metric in a second. It doesn't really mean anything right now. It's just bits of information different from our optimal coverage. But we also have results for the optimal delta V case. One interesting thing to highlight is that the optimal delta V configuration versus the optimal UV configuration varies by several orders of magnitude. So there really is a difference, or a meaningful difference in what is our best coverage and what is our best from the propellant mission objective perspective. So to contextualize the UV coverage of these 2 constrained optimization points, I'll just go ahead and put these figures on the screen. The top one is our best case. You can see it's relatively covers the entire area. It's relatively uniform. There's some gaps at the extremities, but compared to this minimum delta V case here, it's significantly different. So the image quality we would get from these 2 would be significantly different. This is, again, just to contextualize that there's not just small differences that we're talking about here. It's fairly large. So let's look at a couple of actual the solutions. We looked at this in objective space, let's look at this in solution space. So this is all of the results for the best UV coverage in the constrained case. So this is the UV plane coverage we just saw. We'll start looking at the absolute orbit. As I mentioned earlier, our circular orbit projects onto the plane as an ellipse of some sort. In this case, it's almost just a straight line because the solver found an equatorial orbit for the UV plane coverage. Interestingly, it's a lot of these spacecraft grouped together, but there still is separation by the safety constraints in the RT plane. I think what's more interesting, I'll kind of skip ahead here. What's more interesting is the difference between the unconstrained, this is the minimum delta V solution without safety constraints. And you can see the solver finds all of the x components of the relative inclination vectors to be 0 to eliminate the delta V contribution from a non-zero relative inclination. And a lot of the relative eccentricity vectors are hovering near 0. This is to be expected. This is something that's telling us that the solver is finding behavior that we know from the models to be low delta V relative orbits. But these are not safe orbits or practical. These spacecraft clustered in right here are not guaranteed to not run into each other. But if we constrain the problem and then optimize for delta V, we get this high density, safe formation, still with relative inclination vectors all on the y-axis, this time though with a better distribution of relative eccentricity vectors to guarantee passive safety. Also, I didn't highlight this before, but the orbit is polar. This isn't great for launch considerations, but in terms of delta V, this is going to eliminate our drift due to J2, our RAN drift due to J2. So both of these orbits are polar. This one is just tilted a little bit, or the RAN is shifted a little bit to change the UV plane coverage. This is a lot of information, and it's kind of hard to show these results without getting into the nitty-gritty, but that is what I had. So to kind of conclude, this sort of study with many spacecraft in a swarm for interferometry and image UV plane coverage, I don't think it's been done at this scale, and it hasn't really been looked into because formation flying is starting to take off. It hasn't been feasible in the past. But this is kind of a budding research area that I know Professor D'Amico and I are very excited about. So there's a lot of future work to pursue, including continuing picking up on this formulation for UV plane coverage, it's a little bit more conducive to optimization. The problem right now is really non-convex. The loss formulation, or the loss landscape is not very kind. So reducing the problem further may be beneficial. There is some work to do on passive safety constraints. How can we reduce this combinatoric explosion in the number of spacecraft? Evaluating off-nominal swarm configurations, because I didn't mention this, I'm not sure, but we evaluated UV coverage only in the two-body problem, whereas J2 perturbations can actually improve your measurement sampling distribution because it'll change the orientation of the spacecraft. But finally, I really wish I had images to show you guys where we simulated image reconstruction from the measurement sampling, but that's going to be left to future work. So that was a long rundown, but that is all I have. I would appreciate some questions.